morning, everyone. How are you all doing today? How was your weekend?
I went to a Ukrainian protest rally thing.
Oh,
For
here in the area?
yeah, in Sacramento. It
Yeah.
was yesterday downtown.
Wow. How many people came?
A lot, like a lot, like a couple thousand.
Are you Ukrainian?
Yeah, I'm Ukrainian.
Yeah.
I'm over there right now, and also like the company that I work at and my dad's company is has a lot of employees over there right now, so it's like a little bit of a tough situation. But
Yeah. Do you have friends and family there?
yeah. So I have my cousins are over there. My aunt is over there. Most of my family's out of the country. They've like, lived out of the country. I have family in Italy and Germany, but other than that,
Wow.
well, we're close to the Romanian border, so it's not an issue.
So you said that they've crossed over and they're no longer in the country?
They've crossed over a while ago, like
Oh.
10 years ago. They're good.
Yeah. But still, it's just a tough situation all around, huh? I'm sorry to hear that.
But
I'm sorry, I missed what you said.
it's a little tough, but there's no one's lives are in danger currently. So.
Yeah. But they probably have friends and relatives still in the country.
Oh
or-
yeah. Plus the fact that some are getting drafted for the war.
Yeah. Do you wish you were over there helping, or are you good here?
I wish I could help. I don't like participating in war, but like I've donated. I've done as much as I could from here.
Yeah.
And yeah, but I wouldn't want to go to war though. That is not a fun experience. Like any kind of just risking your life for pointless political gain of some dictator.
Yeah. Well, I've been trying to follow all the news and keep up with what's going on.
Yeah, Ukrainians are making a really good defense in a way.
Oh, absolutely.
No major cities, not a lot of casualties on our side, but it's pretty heartbreaking to see because it's like the country's falling apart. There's like no, even if Russia were to like quit today, businesses have closed, our economy's done, everything is like gone to a place where it's really hard to bounce back from.
You mean just over the past week that's happened, or?
It's been and before that, just from like the constant pressure of like the Russian government always trying to like control like Ukrainian politics. And it's been like at a casual like decline since the 90s, but it's like the peak of it.
But do you think this is the start of something bigger, or do you think it's going to kind of end here?
I have no idea. It all depends on how Putin wants to react to the news of him not making any progress. How much of like how much of a reaction he's going to have, because he's threatened like nuclear war basically for the world. Like
I don't know. That may just be talk.
I hope it's talk. Very much hope it's talk. But I don't think it's going to spiral into something more, because he would be really dumb to try and attack any other nation, or try and do something even more aggressive. Because already he's like the Russian economy's fallen. The people are not in support of. Well,
they're being told something entirely different.
Yeah. They have the propaganda that's like shifting their worldview, but they're clearly not in support because they have like no access to their money now, no access to any kind of like resources outside of Russia. Like just recently SWIFT was closed and people are trying to like furiously withdraw money from their banks, which you know how that ends. Banks don't have enough cash to support the accounts. So Yeah, I just hope it ends quickly and that there's not like a lot more death because Russian civilians are being killed over this too. Like not civilians, but like young people my age that are not politicians, not anything. They don't have like hatred against other people. They're just being told orders of like, oh, you have to go attack Ukraine,
Hmm.
and they can't say no because they've signed a contract. And I don't want them to die either because they're still like, how do I put this? Like Russian people and Ukrainian people are very, very close to each other, but the
Right.
governments and the politics are completely different. And I don't want like a Russian person dying just because a politician has told them
Yeah.
to go kill someone else. It's
What,
not.
what do you think his end game is? Because it's easy
I
for
think
a leader to just give the orders and the tanks roll, but then, if you do end up taking territory, then the hard part really comes with rebuilding
oh,
and,
he's
you know,
it's a dumb like attack from the beginning because like the Ukrainian people, we've been like throughout history, we've been taken over by other we've been taken over by Poland, Romania, the Austrian Empire at one point, then Russia, of course, but we still remain the Ukrainian people. So it's not like he's going to try and convert us into like the Russian people.
yeah,
It's not going to work.
yeah,
Even if he does take over it, it's not going to be like a peaceful living situation or like an easy one to like control. So just from that alone is a dumb decision to try and overtake the country. Um, I don't know what he sees in Ukraine as like because after war usually there's nothing left. There's no factories, um
no
no like
schools, no
no
still,
schools, no
yeah,
nothing to like enrich your own people with
hmm,
it. It's just land. And land wise, Russia has tons of land that is just as undeveloped as a war torn country would be. So I don't see the point, but he sees something in it. I don't know. I think it's just the like the
he wants to live the glory days of the old Cold War.
yeah,
Like,
yeah, yeah. He wants the glory days of the Soviet Union, but that's never going to happen again.
I mean, once you have a country that's been free for what, 30 years,
Yeah,
it's kind of hard to go back.
it's impossible to go back. I don't know why he's trying, but yeah, Ukrainian people are going to try and defend as much as possible. It's good.
Basavaraj on YouTube says, "Is your family safe?" I think you
Yeah,
answered
my
that.
family, like my immediate family, is safe. Except for one aunt that lives in Ukraine still. She's so close to the Romanian border, so like literally a half an hour car drive
Mm.
from the Romanian border. It's not an issue, and the city that we grew up in was what's it called isn't like a major city that people try and attack or there's no like if you conquer a city, you're not going to get any kind of like strategic benefit. So
Yeah,
there's literally there hasn't been any Russian troops in our city at all since this started. No bombings, no nothing.
because they're not
So
entering from that
no. It's
direction.
like the complete opposite side of where the Russian
Mm.
border is, or from where Belarusian border or anything. Um, so we're safe, but we do have family friends that are going to war. So
Wow.
it's not that fun.
Well, we'll keep them in our hopes and prayers that
Yeah,
everything is going to turn out well.
yeah. It's just a situation that's just like it's like a nightmare almost.
How are
It's
you
like
doing? Like,
me
yeah,
personally, I'm good.
you're good.
I'm not too distraught over it. I am like sad, very deeply saddened, but
Yeah,
I don't have like major life changes other than like having to pick up a lot more work. Because we have people that usually would do the work like for my dad's company in Ukraine.
hmm,
I'm having to pick up some of that work because we don't know the future of how it's going to go down.
but I would just point out to all of my students that if this is stressful for you, if you're feeling like you need to talk to someone about it, our college does have resources available, and you can reach out, and then we can connect you with, people that, for whom that this is their job, right, is to help out students who are feeling stressed about these sorts of things. So, not just for you, but for anyone who's
Yeah, I know.
listening.
Everyone. Yeah, good. We have a good college. I really like Sierra. Sierra's great.
Well, we can turn our attention away from the problems of the world and
Back to computers.
talk about computer science and stuff like that. So we're beginning at chapter 6, and chapter 5 was about modular arithmetic and learning to do some fundamental operations with modular arithmetic. But now we're turning our attention to chapter 6, which has more modular arithmetic stuff, but kind of from a different angle. And so we started talking about the shift cipher and the linear cipher last time. The shift cipher, is a very basic cryptographic system. There's not a whole lot to it. The linear cipher is more interesting because it combines two operations, addition and multiplication. Decoding the shift cipher is super easy. All you have to do is just subtract off the offset, and then you're back to the letter that you were at. But with linear cipher, you got this problem where you can't just subtract off the offset and then divide out the multiplier that you multiplied in to begin with. So let's take a little review for people that maybe haven't fully watched the videos about the linear cipher or were here last week. And let's just go over this quickly. So the linear cipher is you take the plain text and you multiply it by a multiplier and add an offset. And then you do mod n, and that n there is the size of your alphabet. In this case, it's 26 because there are 26 letters at least in the alphabet we're using here. And so very quickly, let's do an encryption. So we'll start with a plain text. Something short, 4 or 5 letters. I don't know, what word should we use?
Ukraine.
Ukraine? It's a little bit longer than I had hoped. Why don't we go with, I don't want anything to remind us about what's going on in the world. Something happy and upbeat. How about this? Let's do music. We'll do that. That's our 5-letter word we're going to use. So we're going to convert that first into numbers. We've got 12, and then 20, and 18, 8, and 2. And then in order to do an encryption, we need our secret key. It consists of 2 numbers, the multiplier and the offset amount. So let's go ahead and pick those numbers. Does anybody want to use for a multiplier? Yeah, just pick a number. 2. How about a better one? I'm sure we can do better than that. 28. So actually, here's an interesting question. What are good values for a multiplier and an offset amount? What are some reasonable values?
A prime number?
So primes are good, but let's first start trying to figure out what's a good range of numbers we can use. Like, what's the minimum number we could use, and what's the maximum number we could use? Now, obviously, we could use any number that we want, but there are numbers that are better than others. Can you try to could we use 0 as the multiplier?
Zero wouldn't work. It would be 2. Well, everything would turn out to be 0.
Yeah, so you multiply by
No.
0, and then everything would just be whatever the offset amount is. So clearly it has to be bigger than 0. What about a maximum number? Since we're dealing with modular arithmetic, if we choose a number like 28, well, multiplying by 28, remember we talked last time about the properties of modular arithmetic. If you multiply by 28, that's equivalent to multiplying by 28 mod 26, which is 2. So multiplying by 2 and multiplying by 28 are really the same thing. So what does that suggest to you about the maximum number that m could be? I mean, it could be any number, but what's the practical maximum number?
$26.
Yeah, or actually 25, because multiplying by 26 is the same as multiplying by 0. So it should be less than n, our modulus amount. And what about k? Could it be 0? Sure, it could be 0. I mean, it's not going to do anything harmful to our encryption, but it's not terribly useful. But still, it could be 0. It doesn't result in like a bunch of weird numbers coming out. And what about its maximum number?
Would it also be 25?
Yeah. So that should also be less than our modulus, because adding 26 is the same as adding 0. So it just cycles around again. Okay, so given that m needs to be positive and less than our modulus, and k needs to be 0 or more and less than our modulus, let's pick some numbers for k and m. What would you like to use for m?
5.
5. Okay, we'll go with 5. And how about for k?
7.
7, all right. Okay, so we're going to do 12 times 5 plus 7, and 20 times 5 plus 7, 18 times 5 plus 7, 8 times 5 plus 7, and 2 times 5 plus 7. Can you help me out here? What are these numbers? I think this first one is 67. Next one is 107.
97.
97. Okay. This one's 47. And the last one is 17.
17.
Multiplying by 5 is easy. And then we'll do a mod 26. So we end up with, let's see, 67 mod 26. Python can help us out with this. So 67 mod 26 is 15. 107 mod 26, 3. 97 mod 26, 19. 47 mod 26, 21. And 17 mod 26 is 17. So we end up with P, D, T, V, and R is our encrypted word after encrypting music. So I'm interested in knowing, like, what would result if we kind of mixed up the values of m and k? So we know here that m needs to be between 0 and n, and k needs to also be between 0 and n. So let's just come up with a variety of values for these two and see what happens. So why don't you just like put in the chat, just put in like pairs of numbers. What would you choose for m and what would you choose for k? And then I'll just write some of them down and then we'll see what happens. Okay, so we got 3 and 3 is one pair. 3 and 7. 6 and 9. 1 and 1. Okay. 9 and 13. 8 and 5. 11 and 5. Do one more. 7 and 9. Okay. So what I want to do with this is taking a pair of numbers, I'm going to write a quick little Python program that will basically calculate the entire table of letters. So starting with A through Z, find out what the equivalent numbers are for each one of those plain text letters. So we're basically going to encrypt the entire alphabet and see what happens. So remember there's the ORD function and a CHR function for converting from ASCII to a letter and from a letter to ASCII. So, well, actually, the first thing I can do is do something like this. I can go for, let's go C in range 0, 26. So actually, not C. This should be P. For P in range 0 to 26. So I'm going to range P from 0 up to 25, and then I'm going to calculate C. Actually, up here, right up here, I'm going to go M equals 3 and K equals 3. And then I'm going to print P and C. And let's see what happens. Okay. So I've got the first column here is our plain text values from 0 to 25. And our second column are the ciphertext values. So in addition to the numbers, I also want to display the equivalent letters. And in order to do that, I'm going to need to use the CHR function to convert from the number into a letter, but it needs to be the ASCII values, which start at 65, not at 0. So I need to offset all of those by 65. So let me go ahead and print out P plus 65 and C plus 65 converted to ASCII, or converted to letters. Okay, so we can see from this table that A maps to D, B maps to G, C to J, and so forth. So that would be the mapping of plain text to ciphertext with a multiplier of 3 and an offset amount of 3 as well. Let's try a different pair of numbers. 3 and 7 was another one I was given. And in this one, A maps to H, B to K, C to N, D to Q, and so forth. Let's try 5 and 7, which was the numbers we were given here. And this one, we can see that M maps to P, D maps to W. Oh, whoops, no, that's not correct. U maps to I. Oh, U maps to D. There we go. I just misread it. And then S maps to T. I maps to V. And C maps to R, which was the encryption that we came up with for the word music. Now, if you were to decode that, if you were to go backwards, all you'd really have to do is come up with this table, and then you can go backwards. So the word was be P, D, T, V, R, and we want to go backwards. So we can find P over here, and we can see that its equivalent letter is M. And then we find D. Where's D? Here it is, D. We go back to U, and then T goes back to S. And here's V, goes back to I. And finally R goes back to C. So we can reverse this very easily and go back to the plaintext just by generating this table that has the plaintext and the ciphertext values right next to each other. So let's keep going. Let's do 6 and 9. Now, do you notice anything here?
Some letter are repeat.
Some letters repeat. Good. A maps to J, but so does N. N also maps to J. And B maps to P, and so does O. O also maps to P. So if I was to encrypt music using this combination of numbers, 6 and 9, I wouldn't be able to decrypt it, because whatever letter came out might have two possible values for its plaintext. Let's try it out. If you do music, you get M maps to D, and U maps to Z, and S maps to N, I maps to F, and C maps to V. But if I then try to reverse that, and I try to do, if I look up D here, where's D? Here's a D, and here's also a D. So D could be either M or Z. And we can't really tell which. Now we could use this idea that whatever word comes out is probably going to be an English word or something intelligible. But every single letter in our ciphertext has two possible plaintext values. And so every word, every letter could be one of two things, which means for a word like music, there's 32 possible quote-unquote words that could be the plaintext. And maybe two of them are actual real words. We'd have to work it out to see if they are. But it's possible that there are two possible words that this could be, and that kind of leaves it ambiguous. So 6 and 9 are clearly not good values to use for M and K.
Is it because both are divisible by 3, and so if you would multiply by 6 and then add 9, it's just like adding another multiple of 6.
All right, so what we're after here is what's the criteria for picking good values of 6 and 9? So we've already determined that 3 and 3 are okay, and 3 and 7 are okay, and 5 and 7 were also okay. Let me write those down here, squeeze them down at the bottom. So those were okay, but 6 and 9 are not okay. So your hypothesis is that since both of them are divisible by 3, that leads to a problem. Let's see if there's other pairs of numbers that obey that same property and also cause a problem. What about 1 and 1? I mean, those are both divisible by 1. Let's see if those work. Okay, 1 and 1 seems to work. They're not all jumbled up like they would be for other combinations, but at least there's no repetition. So 1 and 1 appears to work. Can you come up with two numbers that are both divisible by 3 and aren't 6 and 9?
Twelve and 16.
Let's try 12 and 16.
12 and 18.
12 and 18. Let's try 12 and 18. What do you think about this combination?
I see repeated ones.
See some repeated ones? Let's see if we can winnow this down some further. So maybe it has to do with that not that both of them are divisible by the same number, but they're just that both of them are divisible by 3. So let's try 3 and 3, like the smallest numbers we could do. They're both divisible by 3. How about this one?
Looks good to me.
That one looks good. So it's not that they're both divisible by 3. And some people are posting in the chat there that maybe it's that the greatest common divisor of m and k has to be 1. But in this case, they're both, the greatest common divisor is 3. And this does work. And when we were doing 6 and 9, the greatest common divisor of those were also 3. So this works as well. So it's not divisible by 3, nor is it that both numbers are divisible by the same thing. Let's try some other combinations that we had here. So 1 and 1 worked. Let's try 9 and 13. Does it look good, or does it have repetition? This one looks pretty good. How about 8 and 5? Now already I can see it starts with FNV here, and I see FNV here, so I know that this has repetition in it. So 8 and 5 does not work. How about 11 and 5? And then we'll try 11 and 29 here in a moment. Okay, starts out FQB, and do I see FQB anywhere else? I do not. So 11 and 5 appears to work. We'll try 11 and 29. It starts out DOZ, and I don't see those letters anywhere here. So 11 and 29 works. Well, there's a suggestion that maybe m and k should both be prime. Maybe that's the key thing. Well, for 11 and 29, they're both prime, so that seems to bear scrutiny. Let's try some other prime numbers. Let's see, we did 5 and 7. We already know that works. So let's try, what's a prime number we haven't tried yet? We've done 3. Oh, we haven't done 2. Let's try 2. 2 and 11. What do you think about 2?
Repeat.
It repeats.
Yeah, there's some repetition there. LNP here, and then there's LNP down here. Okay. So actually, there's prime numbers that don't work, but you might be thinking, well, 2 is just like a weird one, right? It's the only even prime number, so maybe that's the thing. Let's try. So we tried 3, we tried 5. We haven't tried 7 yet. So let's go ahead and try 7 and 9. I think were one of the pairs of numbers that people suggested. 7 and 9. And that appears to work. Okay, so far so good. We've tried 11. Let's try the last prime number. Go ahead.
Can we try 21 as a multiple?
21.
Okay, that looks good.
That one looks good.
It seems like it's just even multipliers that make it messed up.
So if the multiplier is even. So maybe it's just they have to be odd. What's another prime number we haven't tried yet? So we did 2, 3, 5, 7. The next one would be 11. Actually, no, sorry, we already did 11. We did 11 and 5. How about 13? Whoa. Well, that's just crazy there. So 13 is prime. It's odd, but well, maybe what if we change k? Like, let's make that also 13. Okay, we still get this. It's not even repeating in like half the letters are one set of values and half are another. It's
26 is divisible by 13.
Oh, okay. So 13 is a factor of 26. So it can't be that they're prime, although the primes happen to work pretty well. For the most part they work, but it doesn't work here clearly for 13. It also didn't work for 2.
So it's whatever is a factor of 26 will cause it to repeat.
Yeah. So it turns out that for m and k, the m value has to be a specific set of numbers. K can be anything. But as long as m obeys a certain criteria, it'll work. So m and n are modulus, must be what's called coprime, which is a fancy way of saying that they share no common factors. So as long as you pick your m, your multiplier, so that it is coprime with n, the modulus, you're good. So coprime is, there's actually two words there. There's coprime and there's relatively prime, and they basically mean the same thing. So you know what a prime number is? A prime number, for those of you who don't know, a prime number is a number that is only divisible by 1 and itself. It has no other factors other than those two. But primeness is a characteristic of a single number. To be coprime or relatively prime, that's a characteristic of a pair of numbers. So two numbers are said to be coprime or relatively prime if both of those numbers share no common factors. They could actually be primes themselves, or they could be actually not primes. As long as they don't share any common factors, they're said to be relatively prime or coprime. So this is going to give us an insight a little bit into how to decrypt this linear cipher. First thing is the m and k have to be, sorry, not m and k, just m has to be coprime to n, and what that's going to do is ensure that our plain text alphabet and our ciphertext alphabet have a one-to-one mapping between them. That for every letter in the plain text, there's exactly one letter in the ciphertext, and vice versa. For every letter in the ciphertext, there's exactly one in the plain text. If that's not the case, if there's some duplicates, then we are unable to unambiguously decrypt it. So that's going to be really important for any cipher, is to ensure that for every symbol or every value in the plain text, there is only one value in the ciphertext. And the reverse also has to be true. For every value in the ciphertext, there can be only one value in the plain text.
because of that, English is a really bad language to try and cipher in a way, because it's not prime to begin with, like the amount
Well,
of letters in it.
well,
But
you
there
see,
are other languages that would have, like, let's say, a prime number of letters in them, so they would be easier to cipher.
and to be fair, you wouldn't really. I mean, we're using linear cipher because it's easy, but it's easy to compute, easy to study. But if you're going to encrypt something like even English, you probably would not just encrypt each letter individually, because you end up then with a ciphertext that has the same distribution of letter frequencies, just the letters themselves are different. So you could then study the ciphertext if someone had encrypted a long enough passage and just look to see what's the most common characters. If you're just looking at text, plain old text, then probably something like space would be the most common letter, most common character, and you could tell which letter was the space pretty easily. If you don't have any spaces in your text at all, or you ignore them, then you're looking at something like E or T or N being the most common letter. Even if it's encrypted, you just look for the most common encrypted letter and you go, oh, that's probably an E or an N or a T. And from there, you can start guessing what the encrypted or what the decrypted text is. So a better strategy would be to do something like encrypt not just single letters, but blocks of letters. Let's say maybe 3 or 4 at a time. That means now your modulus has to be much bigger. You can't just use 26. You now have to use 26 to the 4th for 4 letters at a time. But the same idea. You take 4 letters, you convert them into their numeric values. You somehow scrunch those together to make one giant number, and then you encrypt that. But even that is susceptible to analysis if there is a sufficiently large amount of text being encrypted. Because even with something like 4 letters at a time, you're still going to get common words in there, like and plus a space, or the and a space, occurring over and over and over again. And then you can start going, well, what's the most common letter, what's the most common words, or what's the most common 4-letter sequences in English? And then from there, start guessing what the plain text is. Still, studying linear cipher and learning about the concepts needed to be able to decrypt it are going to be useful as we progress through the more modern cryptographic systems that don't have the susceptibility of being able to be subject to just statistical analysis. So how do you decrypt this thing? So remember, the formula for the linear cipher is C equals P times M plus K mod N at the very end. And so if you just solve this equation for P, then you get C minus K divided by M mod N. And so if you remember our ciphertext from the previous page, we go look it up, was PDTVR using M is equal to 5 and K is equal to 7. And numerically, PDTVR was 15, 3, 19, 15, 3, 19, 21, and 17. Let me flip back. Is that right? Yes. So let's see if we can decrypt this. We'll do 15 minus 7 and divide by 5. And we'll do 3 minus 7 divided by 5. Was that 3? Yeah. 19 minus 7 divided by 5. 21 minus 7 divided by 5. 17 minus 7 divided by 5. Okay, so 15 minus 7 is what? 8. So you got 8 over 5, and this is negative 4 over 5. But the negative is not a problem. We just come up with the equivalent mod 26 number, which would be 22. This is 12 over 5. This one here is 14 over 5. And this is 10 over 5. And here, with everything except the very last letter, we've got a problem. This one's easy. That's 2. But all these other ones here are fractions. And the problem is that we don't have a way to represent. We can't deal with fractions in our modular arithmetic system because we only deal with integers. What do we do about that? So we can't just divide by m because it results in a fraction. And we have no easy way of dealing with fractions in our system. So we need another way to decrypt this without dividing. And so we'll get there. That's what we're going to work on today, which is how do we decrypt this without dividing? So let's turn our attention to greatest common divisor. We mentioned that a few minutes ago. Greatest common divisor is the largest number that can divide into a pair of numbers. So what's the largest? Sometimes it's also called greatest common factor. What's the largest factor for a pair of numbers? And so we might try to solve this problem. What's the greatest common divisor of 30 and 90? And you may have learned how to do this in elementary school or middle school. You might have been taught to do this by successively factoring out numbers and then finding which pairs of factors they share in common. Like you start with both your numbers, 30 and 90, and then you just try to come up with something that divides into 30. 3 and 10. 3 and 10 are both factors of 30. And then we'll try to divide those. You can't divide 3 anymore, so let's come up with, for 10, we'll come up with 5 and 2. And then you can't divide either one of those anymore, so we'll turn our attention to 90. And maybe for 90, we'll do 9 and 10. And then for 9, we'll do 3 and 3. And for 10, we'll do 5 and 2. And then you look at these sets of numbers, and you figure out which of these trees share numbers in common. So I see a 3 here and a 3 here, and a 5 and a 5, and a 2 and a 2, and that's it. So 3 times 5 times 2 is 30. So the greatest common divisor of 30 and 90 is 30. That's the largest number that divides into both. Let's do greatest common divisor of 58 and 60. We'll do it the same way. So 58 can be factored into 2 and 29. 60 can be factored into 6 and 10. 10 can be factored into 5 and 2. And 6 can be factored into 3 and 2. And then we look to see what they share in common. I see a 2 and a 2. And so the greatest common divisor of 58 and 60 is 2. And then for 15 and 26, 15 can be factored into 3 and 5. 26 can be factored into 2 and 13. And these share no common factors. What's the word or phrase to describe two numbers that share no common factors?
Coprimes.
Yeah, these are coprime or relatively prime. So we say the greatest common divisor between these two numbers is just 1. Okay, so somebody asked the question here, this was on the quiz for the class, using the Euclidean algorithm, what's the greatest common divisor of 84 and 24? So why don't we go ahead and do that? So the Euclidean algorithm allows you to find the greatest common divisor without going through this laborious process of coming up with these trees. The problem with coming up with these trees is that they're easy for a human to do, because a human can just look at a number and go, oh, I know 2 factors of that number. I know 2 factors of 30. It's 3 and 10. And then from there, you successively try to factor the resulting numbers until you can't factor them anymore. But it's not so great to be able to program a computer to do something like this, because we're really just doing kind of trial and error, right? Try to think of a number that's a factor and then try to divide it out. If it doesn't work, try a different one. And trial and error is really difficult to program a computer to do. I mean, you can do something like loop from 1 to the number you're trying to factor. As soon as you find one, you divide it out and you start your loop all over again. So you end up doing this loop over and over again, starting at 1 each time until you find all the factors. So again, that's not a great way to do it. The Euclidean algorithm allows you to find the greatest common divisor really quickly. And the way it works is like this. This is, by the way, called a definition by parts. So you take 2 numbers, a and b. If b is 0, then the answer is just a. If b is not 0, then you can compute the answer by finding the greatest common divisor of 2 smaller numbers. This is a recursive function. In order to find the greatest common divisor of 2 numbers, you can find it by finding the greatest common divisor of 2 smaller numbers. So you move b from the second position over to the first position, and the second position becomes a mod b. And then you repeat the cycle again until you finally arrive at the answer. Let's try it out. Greatest common divisor of 30 and 0. So you plug 30 in for a and 0 in for b, and then you evaluate this condition. If b is 0, which it is, then the answer is just a. So here, the answer is 30. The greatest common divisor of 30 and 0 is 30. I can divide 30 by 30, I get 1, and I can divide 0 by 30. I might get 0, but it's still the biggest number that divides into both. Let's try 90 and 30. We already know what the answer is. We know the answer is 30, because we worked that out on the previous slide. But let's try to do it using this Euclidean algorithm. So we plug 90 in for A, 30 in for B, and then we evaluate this condition. So here, first we check to see if B is 0, which it is not. So we move on to the other condition. So we're going to solve this problem. We're going to solve greatest common divisor of 90 and 30 by solving instead greatest common divisor of 30 and 90 mod 30. Which is equal to greatest common divisor of 30 and 0. Right? Because 90 mod 30 is 0. Okay, so now we just evaluate this. We'll plug 30 in for A and 0 in for B, and then evaluate the condition all over again. B is 0, so the answer is just A. So let's do 84 and 24, which was the question that someone asked in the chat. So we'll plug 84 in for A, 24 in for B. Evaluate the condition. B is not 0, so we will chop the problem down into a smaller set of numbers and evaluate that. Okay, 84 mod 24. It's 12. Okay, so now we evaluate this. We'll plug 24 in for A, 12 in for B. Evaluate this condition. B is not 0, so we'll go on and solve this problem. Greatest common divisor of 12 and 24 mod 12, which is the greatest common divisor of 12 and 0. So again, we'll plug in 12 for A, 0 for B. Evaluate this condition. B is 0, so the answer is just A. Okay, let's do one more. Greatest common divisor of 26 and 15. Let me copy this formula to the next page. Well, I'll just stick it down here at the bottom. No, trying to figure out what to do with this. What I'm going to have to do is pull this down and then push this up here. There we go. I like that better. Okay, 26 and 15. So we'll plug in 26 for A, 15 for B, and we get GCD of 15 and 26 mod 15, which is GCD of 15 and what's 26 mod 15? $11. Okay, GCD of 15 and 11. Again, we'll plug in 15 for A, 11 for B. Good, we've got 4. So now we'll plug in 11 for A, 4 for B, and we just do this over and over and over again. See, eventually what we're aiming for is when we do this, keep reevaluating the greatest common divisor. Eventually, the value of B will drop to 0. At some point, it's going to be 0, and then the answer will just be A. So we're evaluating this second expression repeatedly until the first expression becomes true. Let's see, 11 mod 4 is 3. Okay, so we evaluate greatest common divisor of 4 and 3. And this is the greatest common divisor of 3 and 4 mod 3 is 1. So we're not quite done yet, but we can see that these numbers here, these b numbers, are getting smaller and smaller and smaller as we go. So eventually they're going to become 0. Okay, we're almost done. So 3 goes in for A, 1 goes in for B. That means we evaluate this expression again. So we got the greatest common divisor of B, which is 1, and then A mod B, which is 3 mod 1. 3 mod 1 is 0. Now we got the case where A is 1 and B is 0. So the answer is just A. And so this shows us that the greatest common divisor of 26 and 15 is 1. So how much faster is this than doing it the kind of guess and check method? So with this method here, you conceivably have to loop through the factors, the potential factors of these numbers. I don't know how many times, but there's probably some upper limit to the number of times that you have to run this loop over and over again to find all the factors of a given number. Whereas this technique here, you don't have to really run, I mean, you run a loop. You're basically looping until b becomes 0. But the number of steps that you have to do is a lot smaller than the number of steps you have to do using guess and check. Guess what a factor is and then check to see if it is. And if it is, factor it out. So this technique here is a lot faster, and it's working with A and B kind of simultaneously, whereas the other one, you built 2 independent trees, and then you had to run through the trees and find the common factors. So this method here is a whole lot faster. I think maybe next time on Wednesday, we'll get a chance to see visually how this algorithm works. But I'm going to move on to another topic. And that is to learn about the additive and the multiplicative inverse. And this is leading us to the ultimate ability to be able to decrypt the linear cipher without dividing. So let's talk about additive inverse first. And to do this one, we'll focus on regular arithmetic, which means just using ordinary numbers. And then we'll look at modular arithmetic, which is what we really want to be studying. So with regular arithmetic, we got do you understand this terminology? For this notation, for all A, there exists a B such that A plus B equals 0. Remember, the upside down A means for all. It's just a shortcut. Mathematicians are always into coming up with little shortcuts of ways to write things that they use frequently. Kind of like how programmers create functions and constants in their program. If you use a constant a lot in a program, you'll want to make an assignment up at the front of the program that says, every time I see this name, I swap in this value. So I think a lot of people look at these upside down letters and backward letters and they get kind of scared off by the notation. But they're nothing more than just kind of like, I'm going to move it over here, kind of like just constants. Search and replace, if you will. So the backwards E means there exists, and the colon means such that. So we can read this as, for all A's, for all values of A, there exists a B such that A plus B equals 0. So what if A is 3? If I give you a 3, can you come up with a B such that 3 plus B equals 0? So what would the value of B be? What would B B. -3, good. Because 3 plus -3 is 0. Remember, we're just dealing with ordinary, regular numbers here. There's no limit on the numbers we can do. How about A is 8? What's B?
-8.
Good, good, good. How about A is 3/4? What's B?
-3/4.
Yeah, -3/4. That's easy, right? So we can say B is equal to -A. In fact, that's how you usually represent the additive inverse, is you just take the negative of the number you're trying to find. Or if A is -5, what's B?
Just 5.
Yeah, just 5. But now let's talk about modular arithmetic. So same phrase here. For all give values of A, there exists a B such that A plus B equals 0. But now we're doing it mod n, where n is, some number. Let's pick n equals 7, which means we're doing mod 7 in all of our calculations. Okay, A is equal to 3. What's B? What can I add to 3 to get 0 mod 7?
4.
Good, 4, right? Because not A, 3 plus 4 is equal to 0 in mod 7 arithmetic. How about A is equal to 5? What's B?
2.
2. How about A is equal to 4? What's B?
3.
3. So we still use the same notation. We say B is equal to -A, but it's all in mod 7. So really you could just negate the number and then find the equivalent positive number. So if I took 3 and I negate it, I get -3, but its equivalent mod 7 number is 4. If I start with 5, then I can just go -5, but its equivalent mod 7 number is 2. So additive inverse is pretty easy. Multiplicative inverse is going to twist your mind up a little bit. But let's try it. So let's do regular arithmetic first, just regular numbers. For all A, there exists a B such that A times B equals 1. So if I give you A is 3, what's B? Remember, regular numbers. You're not limited to what they are.
1/3.
Good, 1/3. A is 4/5. What's B? Oh, this is easy. Come on. This is 5/4, right? You just take the number and you just reciprocate it. So B is equal to 1/A, but another way to write that is B is A to the -1 power. And this second one here really is the notation that mathematicians use. It's not this 1 over a thing, but rather a to the negative 1 power. So we'll use that one. Now, let's try it for modular arithmetic. Right? It's the same formula, same equation, but we're doing it in mod n. Let's choose n be 7 again. So if I give you a is 3, what's b? What can I multiply 3 by to get 1? Ooh, this one's tricky. It's not a third, because we don't have fractions in mod 7. Is it 8? Abdul says 8. Let's see.
5.
5. What about 5? Well, 3 times 8. 3 times 8 is 24, but we do mod 7 on that. And if we do 24 mod 7, we get 3. So that's not it. Let's try 5. 3 times 5 is 15. 15 mod 7 is, in fact, 1, and that's what we're looking for. So b is 5. Let's try a is 2. What's b?
Four.
Good, 4. 4 times 2 is 8. 8 mod 7 is 1. Excellent. What about a is 6? I can't see you, but I can feel the wheels turning in your head, right? You're running a little loop in your head. You're trying 1, no, 2, 3, nope, 4, nope, 5. What's the value of b? Well, let's see if we can write a program to do this. Like I said, you probably just got a little loop running in your head. So let's try to get that down as a program. Let's run a loop that goes from 1 up to n, or modulus, and tries all possible numbers until we come up with the very first one we find that's equal to 1. So for this program, I'm going to give it a, the number I start with, and n, or modulus. And then we're going to go for b in range 1 comma n. So it could be as small as 1, but could be as big as n, actually n minus 1. And then we'll say if a times b mod n is equal to 1, then just return b. We'll plug in 6 for a, and 7 is our modulus, and then we'll see what it comes up with. And it comes up with 6. Six times 6 is 36. If you do 36 mod 7, you get a quotient of 5 with a remainder of 1. That's what we're looking for. So we can find the multiplicative inverse by just writing a loop. Run the loop from 1 up to n, and as soon as you multiply the two numbers together, and as soon as you come up with a remainder of 1, you found it. So here we're not going to say b is equal to 1 over a, because we don't have fractions. But we can say, we can just define terminology to say that b is equal to a to the negative 1 power, mod n. Because a times a to the minus 1 power is equal to 1 mod n. Right? The two just cancel each other out. So here's where that leaves us. Remember, we had this problem with the linear cipher earlier. We were trying to subtract k and then divide by m, but we couldn't do that because dividing by m usually gave us a fraction. But now we have a tool that we could use to decrypt the linear cipher. Instead of dividing by m, which gives us a fraction, what we could do instead is multiply by its inverse. Remember, the multiplicative inverse is really, you can think of it as being the reciprocal. And the reciprocal is like dividing, right? So if b is equal to 1 over a, it's kind of like dividing by a. But it's really multiplying by its inverse. And it works in modular arithmetic because of the cycle. It doesn't work with regular numbers. Instead of dividing by m, we're going to multiply by its multiplicative inverse. And that's going to let us decrypt the linear cipher, because we'll avoid the whole problem of fractions to begin with. Now, as we saw here, we can write a function that will find the multiplicative inverse. It just starts at 1, goes up to n, and when the first number it finds with a remainder of 1, that's got to be the answer. The problem there is this is more or less just a guess and check. You guess a factor, or you guess a number, see if it works. If it doesn't, you move on to the next one. This is a terrible way to do it because if n is big, we could potentially have to try a whole bunch of factors before we stumble across the one that works. What we really want to do is find an algorithm that can do it quickly. And for that, we're going to need something called the Euler's Totient function. Now, I'll just introduce you to this function, and then we'll continue next time with how do we use this to find the multiplicative inverse quickly. So Euler's Totient function is the number of numbers that are co-prime to a given number. Yeah. So here's the story I like to tell. Like, what must life be like for a mathematician back in in Euler's days, which was what, the 1700s, 1600s, long time ago, hundreds of years ago? What was life like? You know, I can just imagine he probably woke up in the morning, took a cold bath, and then went down to the local pub and knocked back a few. And then, you know, while he's sitting there, goes like, you know, I think I'm going to think about co-prime numbers today. And just starts scribbling stuff down on a napkin and goes, hey, here's a nifty little thing I just discovered. How many numbers are co-prime to a given number? So if I start with a number like 12, how many numbers are co-prime to that number? By the way, Euler's Totient function these days is usually represented by the Greek letter, is this phi or phi? I don't know exactly how to pronounce it, but the Greek letter is usually, this is the lowercase letter, and then the uppercase letter looks like a capital I with a hole in the middle of it. So what I want to know, or what Euler probably thought of, is how many numbers are co-prime to, let's say, 15? How many numbers are co-prime to 15? Well, let's start by just listing them out.
3, 5.
How many?
2 number, 3 and 5.
No, we're not looking for the factors. We're looking for co-prime. So 1 is co-prime to it. 2 is co-prime. Right, so 2 is co-prime because 2 and 15 don't share any common factors. What are some other numbers that are co-prime with 15?
7.
7, good. So 7 and 15 don't share any common factors. Okay, it's not 3. 3 and 15 share a common factor of 3, so we can't use that one. 4 isn't. Oh, wait, no, 4 is. 4 is, let me write it down. 4 shares no common factors with 15.
So it doesn't have to be prime to be a
No.
prime number?
No.
Gotcha.
Two numbers don't have to be prime in order to be co-prime with each other. 5's not going to work because 5 and 15 both have a common factor. How about 6? Does 6 work?
They both have a common factor of 3.
Okay, so 6 is not going to work. 7 we already determined does work. How about 8?
8 works, I think.
8 works, yeah. 8 works because its factors are 2, 2, and 2. And the factors of 15 are 3 and 5. How about 9?
3 again.
Okay, so 9 doesn't work. 10. 10 doesn't work. 11.
11.
11 works. Good. 12.
3 and 4
Yeah, not going to work. 13.
works.
13 works. And 14 also works. And then you don't have to go any higher than that. So, okay, so this is the set of numbers that are co-prime with 15. And we want to know how many of them are there. And there's 8. So the totient of 15 is 8. So we're not interested in what are the numbers, but how many are there. Okay,
What does the totient give us in the end?
well, this is one of those things where Euler probably wrote it down, maybe published it, told his friends, and went, hey, I discovered this thing. It's the number of numbers that are co-prime with another number. And they said, so what? You know, what? So what? Well, it may be one of those things where it got written down and the application of it wasn't obvious at first. And then roll forward about 200 years, and now we've got modern cryptography where we need to find the multiplicative inverse of something really quickly, and this allows us to do it. So by itself, it's not that useful, but it turns out it's incredibly useful for finding multiplicative inverses. We won't have time to show you how that works today, but I'll show you how it works next time. Let's just finish up here with showing some more examples of the totient function. Okay, what's the totient of 14? So let's just start by listing out the numbers that are co-prime with 14. You kind of get 1 for free. You always get 1.
1, 3,
3, good.
5, 9, 11.
9 and 11, good. Any others?
13.
13, good. Okay, so there are all the numbers, and there's 1, 2, 3, 4, 5, 6 of them. Let's try the totient of 13. So you get 1 for free. Does 2 work? Two works. 3? Yep, that works also. 4 also works. 5 works. In fact, all the numbers less than 13 work because 13 is prime. Since 13 is prime, it has no other factors other than itself and 1. And so all the numbers less than 13, remember you get 1 for free, so don't worry about that one. All the numbers less than 13 work. And when you're dealing with prime numbers, really 1 is not considered to be a factor. From a really like pure point of view, 1 is not considered to be a factor of another number. So don't worry about 1, and you're always doing it less than 13, so you don't worry about 13 either. So all the numbers less than 13 are coprime to 13, and there are 12 of them. What about the totient of 11?
Oh, 10 numbers
Yeah,
going
it's
to 11.
It's going to be 10, right? How about the totient of 37?
36.
36, good. So if n is prime, the totient of n is just n minus 1. So that makes it easy to figure out the totient of a prime number. You just subtract 1 and you've got it. So there are a whole bunch of properties of the totient function that have been discovered over the years. Only 3 of them are important for our purposes. Here's the first one we just came up with. If n is prime, then the totient of n is just n minus 1. So when you're dealing with just numbers in general, you've got prime numbers, and then you've got what are called the composite numbers. The composite numbers are ones that are the result of the product of 2 prime numbers, 2 or more prime numbers. So you've got your prime numbers, and you've got your non-prime numbers, and the non-prime numbers are also called composite numbers. So these 3 properties here give us the ability to find the totient of any number, whether it's prime or composite. All you need are these three rules, and you've got all the numbers covered. Like I said, there are other properties that have been discovered over the years, but these are the 3 that give us the ability to calculate the totient for any number. Throw any number at us and we can calculate it using this. So if n is composite, that is n is composed of 2 factors a and b are co-prime to each other, which means that they're not multiples of each other and they're not they are not the same number, then we can break apart n into a and b, it's 2 factors, and they compute the totient of each one separately. So let's try that out. Totient of 55. We can break that into totient of 5 and 11. 5 and 11 are co-prime to each other, and in fact, they're both primes. And we know how to calculate these. You just plug them into the first property. 5 and 11 are both prime, so this is just 5 minus 1 times 11 minus 1, which is equal to 4 times 10, which is 40. So the totient of 55 is 40. Easy to calculate. Let's try totient of 35. We can break that up into 5 and 7. Those are both prime themselves. So we get 5 minus 1 times 7 minus 1, which is equal to 4 times 6, which is 24. Yeah, I'm leaving you on a cliffhanger. So this is the last one we're going to do, and then that's it for today. And then I'll show you how to apply this to the problems we've been trying to solve. All right, so property number 3 is if n is basically has a prime factor that's repeated. So if n can be represented by a single prime number raised to some power, where that k, and then z plus is just a shortcut for positive integers. Okay, so if n is p some prime raised to some integer power, positive integer power, then you can calculate the totient of that number using this formula. So this is the most complex one here. So we've got prime numbers, we've got composite where the two factors are relatively prime to each other. And the key thing there is they're not the same, right? So you can't do like 3 times 3. That's covered by this third case where you've got the prime factors that are repeated. So totient of 125 is the totient of 5 to the third power. Here we've got our prime raised to some positive power. And that's equivalent to the totient, that's equivalent to this formula. P minus 1, which is 5 minus 1, times 5 raised to the second power. Right, so the 5 got plugged in right there, and it got plugged in right there, and then k got plugged in right there. So this is equal to 4 times 25, which is 100. And here's the last one we'll do, 75. 75 can be broken down into 3 times 25. So this is a totient of 3 times the totient of 25, because 3 and 25 are co-prime to each other. That allows us to now break them apart. And now we've got 3 minus 1, which is totient of 3. And then totient of 25 is this property. We got 5 minus 1 times 5 to the, what's it, 2 minus 1. 2 minus 1 is just 1. So this is not 3, this is 2 times 4 times 5 to the first power, which is equal to 40. So with these 3 properties, you can calculate the totient of any number. All you really have to do is just factor it into its prime factors. With the prime factors, you can apply the first property. With the remaining factors, the ones that are, with the prime factors, as long as the factors are different, you can use the first property. If any of the factors are repeated, then you apply the third property. And it's that second property that just says, basically, we can split it up into its factors. So for this one here, we came with 3, 5, and 5 as its prime factors. We handle 3 as a prime factor, and the repeated 5s we handle with that third property. Any number, you can compute the totient. So with this totient, as I said earlier, this will allow us to find the multiplicative inverse of a number. And we can do it quickly, rather than repeatedly trying factors over and over again. So the question is, what would the totient of 169 be? 169 is 13 squared, so we would apply that third property. Plug those numbers in, and we get the number out, get the value out. So what do you end up with there? 13 squared minus 13. There's actually a couple of different ways to write that formula. This is one that works for me. There's another way that actually involves some division, and it so happens that the factors you're using when you use division, even though it looks like you end up with a fraction, the numerator and denominator have common factors in there, so you always get an integer out of it. So there's a couple of different ways to do this calculation, but this one works pretty well. Okay, so again, sorry to leave you on a cliffhanger. We'll come back on Wednesday and we'll see how to apply all these principles, the multiplicative inverse, the totient function, and what else did we learn today? I'm looking back at the Euclidean algorithm, greatest common divisor, all that stuff to be able to decrypt a linear cipher without using any division at all. All right?
Yeah, on Wednesday, Professor. Great lecture.
Oh, thanks.
I hope you have a nice day.
Yeah, you too. I'll see you next time. Take care, everyone. Bye-bye. Hey, folks on YouTube. Glad you came along. I'm also glad to see that we're getting more and more people every week. When we started out this semester, we had like 1 or 2 people watching this, but now things are getting really interesting. I love this part of the course because talking about the cryptography stuff is like so interesting, and it's nice to see how all these pieces come together. And although the formulas for doing cryptography are not that complicated, there's all the research and the math that had to go on and learned over hundreds of years to get to the point where we can now do these things with these huge numbers. Abdul, you said, what I want to know is, and then, do you have a question? So you want to know how to find the totient of 169? Yeah, go ahead and type in the rest of your question. Because I don't think the answer is 156. I don't know. Let's plug it in. Let's go ahead and try it. So totient of 169, totient of 13 squared. And then we're going to plug that into the third property. So we get 13 minus 1 times 13 to the 2 minus 1 is equal to 12 times 13. Oh, it is 156. You were right. Oh, you just want to know how to decode. You want to know how to decode the linear cipher. There's actually another obscure, almost obscure little formula that I think, did Euler also come up with it? That uses things like the totient function. So it's not the totient function itself that lets us find the multiplicative inverse. It's plugging that totient function into another calculation that allows us to find it. So I think it's called Euler's little theorem. Let me look it up. And that'll give you something to research between now and Wednesday. Where's my notes on this? Yeah, Euler's theorem. One of his many theorems. But Euler's theorem, you plug the totient into that, and it poop, out pops the multiplicative inverse. So that's it for today. again, a bit of cliffhanger. Look up Euler's theorem. And actually, I'm just going to make sure that that is in fact the name of it. Yeah, Euler's theorem. And again, it was one of those things where it didn't seem to be useful at the time, I'm sure, but now it's incredibly useful. One of the underpinnings to modern cryptography. All right, well, I have to end it here. I got stuff to do. So come on back on Wednesday. We'll learn how to decrypt the linear cipher and also start getting into modern cryptography. And spell Euler's. Well, you know, when I was in school, we could never agree on how to pronounce it. Was it Euler or Euler? Like Euler, like someone who wields an oil can? Or is it Euler? So I think, you know, since then I've learned it's pronounced Euler. But let's see, how do you pronounce Euler? Euler, Euler.
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 That's what it says.
Euler.
Vegan says, oil be the judge. Anyway, have a great day, everyone, and be safe out there, and enjoy the rest of your night if that's the time zone you're in. And I will see you on Wednesday. Bye-bye.